Welcome to the Logic Videos. I'm Scott Aikin. This is a video about how to compute truth tables for finding validity in arguments in propositional logic. What we're going to do is we're going to look at a full truth table, and then we're going to look at a kind of a shortcut truth table, what are called incomplete truth tables, where you don't have to compute all the variables for all of the major operators for the argument's premises and conclusions, because you just need to compute the ones for the relevant considerations. So let's start with two arguments. We're going to look at one and then argument two. Argument one is if not R, then not S, so not R. Again, what we are doing with the truth table is we are determining whether or not the truth of the premises guarantee the truth of the conclusion. So, and in this case, it's a semantic test for validity. So it's whether or not the truth of the premises guarantee the truth of the conclusion by the semantics of the logic. We represent that, again, with the semantics of the connectives, in this case, conditionals and some negations. So let's start off with the base truth table for this, R and S. R, S, because we've got two propositions in there. We'll need a truth table of 4 lines. So we'll have R have 2 truths and 2 Fs, and then S alternate TF, TF, and then premise 1 is not R, horseshoe not S. So that's premise 1. Premise 2 is actually provided with our base column here, and then we'll have our conclusion here, not R. So let's go ahead and do our computations. So not R is going to just be F, F, T, T. No problem there. There's no great mysteries about that. Premise 2 is just going to be whatever the base truth values for S are going to be. And so in this case, not R, horseshoe, not S, so we just need to flip them. So that's going to be F, so F, F, T, T, and then we switch the S's, so F, 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 T, F, T, and so a TT gives me a T, TF gives me F, FT gives me T, FF gives me T. Okay, so far, so good. So I've got 3 columns of truth values. So the way that we determine whether or not the truth of the premises guarantees the truth of the conclusion is whether or not there are any instances where you've got true premises and a false conclusion, or a false conclusion and true premises. So what we're going to do is we're going to start, because looking at the conclusion is easiest. There are 2 places in the conclusion where you got a false conclusion. Got a true conclusion? The promise isn't totally relevant to that, right? The only we're looking for is to see if we've got instances where there are true premises and a false conclusion. That's a case of a counterexample to show that an argument is invalid. If you can't find a counterexample, that means that you've got a valid argument. So what we're doing is we've got all the possible combinations of truth values here. We're going to see if we can find a counterexample. Again, true premises, false conclusion. So we got false conclusions here. Let's see if we've got true premises. We got true premises. And in this case, so notice, by the way, in this case, we've got a false premise here. So that one's okay. But notice, by the way, that we have a false conclusion, true premise here, and a true premise here. That is a case where we've got a counterexample. We have an instance where the premises are true and the conclusion's false. So the argument, any argument that takes this form here is going to be invalid. Why? Because we've provided a counterexample with line 1 of that truth table. Okay, so we've shown how to be able to find an invalid argument. What you do is you construct a full truth table, and then you hunt around in the truth table to see if you can find instances where the premises are true and the conclusion's false, where the conclusion's false and the premises are true. Order of that doesn't matter. So what we've got then is a method of showing invalidity, finding a counterexample. Again, counterexamples are instances where the premises are true and the conclusion's false. Well, that was with 2. Let's look at a case where we've got an argument with 3 constants in it. P, Q, and R. So if P, then if Q, then R. If P, then Q, so unless not P, R. Okay, so here what we need to do is we need to put it all up. So let's do that. So we have P, Q, and R. P horseshoe, Q horseshoe R, P horseshoe Q, and then our conclusion is not P, vel R. Okay, so far so good. We've got everything set up. Let's provide our base values for the table. Again, because we've got 3 constants in there, we need to be able to provide a table with 8 lines, okay? So that means 4 T's here, then 4 F's, 2 T's, then 2 F's, 2 T's, 2 F's, and then you alternate, TF. Divide our table in half. Top half, the P's are all true. Bottom half, the P's are all false. Okay, so in this case, what we're going to do is we're going to try to find ways that we don't have to compute all the truth values there. That's a lot of computation. So what we want to do is find ways to be able to sort of shorten the distance and sort of provide whatever relevant lines we need to provide. What I'd like for you to do is start by looking here at the conclusion. Disjunctions are really hard to make false. It takes a very special kind of disjunction to make it false. You need to have a false-false disjunction. So in cases where you've got a disjunction as your conclusion, start there because it's going to narrow the number of lines that you actually have to compute. So we're going to provide the truth table, a full computational truth table for the conclusion, and then we're going to see from there what lines we actually need to look hard at. So notice, by the way, that in every instance where P is true, we're going to get an F on that left-hand side of that disjunction. But notice, by the way, that every time that P is false here, we're going to get a true on the left-hand side of that disjunction. And as a consequence, the disjunction comes out as true. Okay? So those are true conclusions. So as a consequence, we don't have to look for counterexamples there, right? So we just eliminated 4 lines that we don't even have to compute for our premises because the conclusion ended up true. Not going to be a counterexample, not relevant to our search. In this case, so we still need to compute the other side. So R is true, false, true, false. So in this case, we've got an FF. That gives us a false conclusion. FT gives us a true. FF gives us false. FT gives us true. So what are the only lines in our conclusion here on the truth table that we need to look at? The answer is only 2. Lines 2 and 4 are the only lines that we actually need to look at on this truth table, because those are the only ones where we've got a false conclusion. Again, what we're doing is we're looking for counterexamples. We're trying to put the whole truth table together and see if there are any counterexamples that we can find in there. Given the fact that this is not in the form of a counterexample, we've got a true conclusion, we don't need to look at the premises. The only time that we need to look at the premises is if the conclusion is false, okay? And the same thing goes, by the way, with the premises. The only time that we need to look at any more premises or the conclusion is that if we've got a true conclusion. If we've got a false conclusion, don't need to look at anything else, okay? So already we're starting to strategize just about how we fill in this truth table. Given the fact that now that this whole bottom part has got truths in the conclusion, we don't need to look at any of the truth values for the premises. Moreover, in lines 1 and 3, because the conclusion's true there, we don't need to look at the premises there. Only lines 2 and 4 are the places where we actually need to look for the premises being true. So now let's take a look at P horseshoe Q. P horseshoe Q, in the case of this premise, that's a true to true, so we get a true premise. And in the case of line 4, that's a true to false, that's a false premise. Okay, so recall again that because we're looking for counterexamples, we're looking for instances where we have true premises and false conclusions. Now that we found a false premise here, we don't need to look anymore because, again, that's not relevant to whether or not it's fitting our pattern. Doesn't fit the pattern for counterexample, don't have to look anymore at it. So now, so far, I've got a false conclusion and a true premise. So we only now need, with this big complicated one here, we only need to look at one line, right? We only need to look at line 2 to see if it comes out. Because again, The only place where the pattern actually emerges is here with these two connections. So let's do the truth. Let's do it. So Q horseshoe R is TF. So that's F for that one. P is true. So that's true horseshoe F, and that comes out as false. So as a consequence, we are not able to find a counterexample on this truth table. Why? Because in all these cases, lines 1, 2, and then 4 through 8, those are all instances where the conclusion's true. Not going to be a counterexample. Doesn't even matter what the premises look like. So we only needed to look at lines 2 and 4. We looked at lines 2 and 4. Premise 2 came out as true in line 2, false in line 4. Don't need to look at premise 1 for line 4 because premise 2 was false. So we only needed to look at premise 1. In this case, premise 1 came out as false in line 2, and so as a consequence, there are no instances where the premises are true and the conclusion's false, and as a consequence, we then know that this argument is valid. No counterexamples, can't construct or find a counterexample, means it's valid. If you can construct or find a counterexample, it's invalid. So as a consequence, what we've got here with the truth table test, both the full truth table test, where we compute all the lines for all the major operators for the premises and conclusions, or this shorter or incomplete truth table test, where you only compute the ones that are relevant to us finding the pattern of false conclusion, true premises. So long as you can find cases where you break the pattern, in this case, true conclusions or false premises, you don't have to compute the rest of the lines with the indirect truth tables, or not the indirect, the incomplete truth tables. Once we've been able to put this together, we're able to show that there's no possible way for the truth of the premises to be for the truth of the premises to obtain, and the truth of for the premises to be true and for the conclusion to be false. There are no counterexamples, so that argument's valid.